Hey everyone, welcome to Quantum It, where AI, tech, and finance collide to shape tomorrow. If you are ready to think ahead, then you are in the right place. Let's dive in.
Good afternoon, everyone. Before I start today, I'd like to thank you, all my co-authors, for their continuous collaboration and effort. I'm Rajkumar Mehkala, and along with my co-author Sandeep Kumar Pedapalli, we are excited to present our work titled Intrusion Detection with SHAP Explainability and Feedback Loop, a modular pipeline for cyber threat classification. We are thrilled to share our approach, key findings, and how this framework enhances cybersecurity through explainable AI. Let's talk about the motivation. So, what motivated our research was cyber threat attacks today are becoming smarter and complex every day. Traditional based intrusion detection systems are not able to keep up with zero-day attacks, like even and constantly changing threat behaviors. Even AI-based systems are having their own issues. Like most are static and act like black boxes, and those are not flexible enough to adapt. So in our work, we set out to build something different. A system that's not only accurate but also interpretable and adaptive to evolving cyber threats. So based on those challenges, here what our contributions to the field. Like prior works have used SHAP and LAB to add transparency, and some studies hinted that at retrainable ideas pipelines. But what we found was missing a unified framework that combines high performance classification, deep interpretability, and adaptability into one modular pipeline. That's the gap we aim to fill. Our contributions are fourfold. First, a modular framework that can be adapted into different models. Second, a SHAP-based explainability which offers per instance insights. Third, a feedback loop that allows dynamic retraining as new threats emerge. And the last one, extensive benchmarking on the CIC IDS 2017 dataset, which validated our approach. Next, look at the dataset we used to train and evaluate our system. We used Canadian Institute of Cybersecurity Intrusion Detection Evaluations dataset, which contains nearly 6 million flows and 86 features across 15 classes. This dataset realistically simulates both benign and attack traffic. One major challenge is class imbalance. For example, like the benign class has more than 2.2 million samples, while the heartbleed attack has only 11. This imbalance is a key reason that integrated a feedback loop. You can see the class distribution bar chart that emphasizes this disparity, where we can see the benign. Before training, we clean the data, remove non-numerical IDs like timestamps, and standardize all the numerical features. We also encoded the labels into integral values and to support multi-class classification. One interesting finding was that many features were highly correlated. So coming to the system architecture, our system follows a three-stage pipeline. First, a data injection and pre-processing. The second, the intelligent core with a trained model and SHAP explainability. And third, the adaptation stage pipeline through a feedback loop. This modular design makes this pipeline flexible and scalable, where new algorithms or new data structures can be plugged in without rebuilding the same system. Moving on, my co-author will take you through the next sections.
Thank you, Raj. Hello, everyone. Coming to the future analysis, here to better understand our futures, we ran Disney on samples of 5,000 flows. So along with this, here the clustering clearly separates the benign traffic from the major attack types. So showing the futures of the discriminative power. So here we also applied SHAP to interpret our models globally. And the summary plot revealed that the features like destination port, packet length, variations, and the average packet size, it were among the most influential. So together these analyses help us to trust and validate the model decisions. Here you can see all the clusters like all the villain on one side and all the major attacks on the one side. You can see all the clusters, those are the different, like all the blue color is this side and the red color is this side. Those are the major attacks, these are the villain attacks, which we can tell you. And yeah, coming to this, we trained and compared two Ansible models. Here, random forest, one is a random forest and another one is the XGBoost. So here both are well suited for the tabular data and integrate seamless with the SAP. So here we used an 80-20 stratified train test bit to maintain the class distribution. So here this random forest used in this random forest used the 100 trees with the entropy splitting, while we can see XGBoost used 100 estimators. So when we take this XGBoost as 100 estimators, we can see here the learning rate of this is 0.1 and the maximum depth of this is 6. So mainly given the imbalance in the data set, so we emphasize the macro average metrics like precision, recall, and F1 score. Yes. Coming to this, both models achieve, mainly in this, both models achieve very high accuracy, I mean above 99.9%, which demonstrates the robustness of the pipeline. However, accuracy alone can be misleading with such imbalanced data. So the more telling metric is the macro F1 score, which balances the performances across all classes, including minority ones. Here, XGBoost clearly outperforms the random forest with a macro F1 of 0.92 compared to 0.90. Yeah, the improvement is, it's looked like very small numerically, but it makes a significant difference in detecting rare attacks. So, based on these results, we selected XGBoost as the primary model for our final framework. So, these confusion matrices highlight model performance across the 15 classes. So both models performed exceptionally well. So here we are achieving 99.9% accuracy. However, XGBoost consistently outperformed the random forest in macro F1 score. So here we are showing better balancing across all classes which we are looking at. Still, some minority classes such as infiltration, SQL injection, X attacks, and misclassified, and these highlights the value of our feedback loop, which can target such weaknesses in the retraining purposes. So here you can see. Here you can see more on the macro precision recall curves. It's comparing random forest and XGBoost. Here, XGBoost had a higher macro AUC of 0.9692 versus 0.9492. It's indicating the better handling of class imbalance. So overall, XGBoost proved to be the stronger candidate of our final pipeline. So coming to the explainability. Yeah, coming to the explainability, explainability was the center to our design when we are doing this thing. Here, the SHAP global summary plot confirmed that the top contributing features, but beyond the global trends, SHAP also provide, for instance, explanation. For example, when a flow is flagged as malicious, analysts can see which exact feature drove the prediction. So this transparency not only builds trust, but also speeds up the investigation process by giving actionable insights. Yeah, here my friend will continue. Thank you.
Thank you, Sanju. To conclude our study, we demonstrated that we built and validated a modular IDS pipeline that combines high accuracy and interpretability and adaptability by using Canadian Institute of Cybersecurity IDS 2017 dataset. Our XGBoost model achieved 99.96 accuracy and a 0.292 micro F1 score. The integration of SHAP explanations and a feedback loop makes the system practical for deployment in real world, including SIM platforms like Google Chronicle, Snap, Datadog, and other platforms. We also aim to test and optimize deployment within the production scale environments. This next step will help us transition our framework from research to practice. Thank you.